Welcome to tutorial 14, where we're going to be looking at the action of a monostable circuit using a 555 timer to create that. If we have a look at this circuit diagram, we should be able to recognize a few things. First of all, we have a switch, so quite clearly that switch is going to be pressed. We have a resistor and a capacitor, so some form of timing is going to take place in this circuit. And then we also have a LED with its current limiting resistor on the output. So hopefully you should be able to see that when we press the switch, the LED, something is going to happen dependent upon the timing of the capacitor and resistor. Let's have a look at the circuit. So in front of me I have the circuit built. I currently have a 100 kilo ohm resistor R and a 100 microfarad capacitor. And I'm going to press the switch and watch what happens. So there we go. We have an LED that comes on for a certain amount of time and then it goes off. It comes on when the switch is pressed. Monostable. Mono means one. Therefore one stable state. There are two states, R high and R low, R on and R off, depending on which way you want to explain it. And therefore, if we have one stable state, we must have one unstable state. Now our stable state is actually when the LED is currently off, because that state is stable because it will not change unless we do something to change it. When the LED comes on, however, it is considered the unstable state because it will not stay on forever. It will automatically go off dependent upon the values of R and C. So let's measure the amount of time that the LED stays on for. Now I also have the oscilloscope plugged into the output so that you can see a waveform happening at the same time, so you get used to measuring DC in the circuit. Okay, so I'm going to press the switch and the start button on my stopwatch at the same time. Go. And I'll press stop once the LED goes off. You can see here that the oscilloscope trace has gone high. So there we go. That LED stayed on for approximately 12.87 seconds. Not absolutely precise because of course I'm not that exact in my starting and stopping. But 12.87 seconds here will do. So I'll enter that result into my table. Next, I'm using a 220,000 ohm resistor and a 100 microfarad capacitor. So I'm going to change the value of the resistor. Okay, so I'm going to press start with the increased value of resistor, go. You see the output of the oscilloscope has gone high again. When the LED goes off, I'll press stop. So I made that measurement 28.57 seconds. So we'll enter that into our table. 28.57, and then finally we're going to go back to our original resistor value and put in a 220 microfarad capacitor. Reset our stopwatch, output on 0, LED off, ready, steady, go. and I made that one 28.31 seconds. 28.31 seconds. Now you'll notice that those two values were pretty close together. Okay, let's go back to our calculator, and as with everything with our 555, there are calculations that you could make. So in other words, if we wanted to design a monostable that had a pulse length of a certain amount of time, we can use the formula 1.1 times the value of the resistor times the value of the capacitor to do that. But what we're doing, we're just checking against our predetermined values. So 1.1 times, in the first example, 100,000, 100 exponent 3, times 100 microfarads, 100 exponent minus 6, equals 11. So that's 11 seconds. In our second example, we have 1.1 times 220,000 ohm resistor, 220 exponent 3, times 100 microfarads, 100 exponent minus 6, equals 24.2. And then in the last example, 1.1 times 100k, 100 exponent 3, times 220 microfarads, 220 minus 6, equals 24.2. So we can see here that the calculated pulse length was 11 seconds. We measured it to be 12.87. The calculated in the second and third was 24.2, and we measured it to be about 28.57 and 28.31. So those values aren't exact, but once again we can put it down to tolerances of all sorts of things: resistors, capacitors, the point at which I started and stopped my switch, and my stopwatch. Okay, let's have a little look at our conclusions. Is the trigger for a monostable a high or a low? Well, if we look at the circuit diagram, here is our trigger pin. In other words, it's a little bit like a gun starting a race. The second you press it, the race begins. And if we look at this, the trigger pin is held high by this pull-up 22k resistor. But the question asks, is it triggered by a high or a low? Well, we actually start the circuit by pressing the switch, and by pressing the switch we connect pin 2 directly to ground. So therefore this circuit must be triggered by a low, because the switch is connected to 0 volts. What does pin 3 output do when the system is triggered? So if we look at our circuit again, when we press the switch, it turned the LED on. For the LED to come on, the output must have been high. And we were looking at that on the oscilloscope as well. Let's have a quick look and see how high that circuit went. Now my volts per division here is set at 1 volt per division. So when I press the switch, the output goes high. We started in the middle, 1, 2, 3, 3.6. But of course that's with an LED connected. If I remove the LED, the output goes even higher, and I have to change down on the scale to see it. So the output actually now goes to about 4.4 volts. So what does pin 3 output do when the system is triggered? It goes high. There's no need for us to put in the actual voltages here. From the results, what happens to the time period if the resistance is doubled? Well, if we look at our results, the occasion when we doubled the resistance, in fact it's slightly more than doubled, we can see that the measured pulse length was again slightly more than doubled. So we double the resistance, we double the pulse length. And from the results, what happens to the time period if the capacitance is doubled? Well, in the first example and the third example, the difference is we've doubled the value of the capacitor. Again, slightly more than doubled. And here, looking at the measured pulse length, we have slightly more than doubled the pulse length as well. So on both occasions, if we double the resistance, we double the pulse length. And if we double the value of the capacitor, we double the value of the pulse length. When you press and hold the switch for longer than one of the time periods, what happens to the output? Well, let's pop our LED back in, even though we can see the output on the oscilloscope. And let's press our switch and start. Now I have a 100k ohm resistor and a 100 microfarad capacitor, so this should last about 12.87 seconds. So we're going to hold it down longer than that. So will it go off whilst I'm holding the switch after 12.8 seconds? Well, we're now a few seconds beyond that time and the LED has remained on. So let's enter that in. The LED remains on. What happens when you then release the switch? Well, let's have a look. So we're up to 34 seconds. I'm just going to take my finger off the switch and the LED has immediately gone off. So the LED immediately goes off. I'm going to show you one other thing to do with this circuit, which we haven't really been able to look at before. I'm going to look at this discharge threshold. Now we know that a capacitor resistor circuit charges up, and depending on the value of resistor and capacitor, depends on how quickly it will charge. But just to explain the discharge and threshold pins, the threshold pin is the important one here, because this is telling the 555 when to turn off. And when the voltage at the threshold pin reaches 2/3 of the 5 volt supply, or 2/3 of whatever that supply is, in our case 5 volts, it recognizes it's reached that value, and then the discharge pin will discharge the capacitor. So in other words, we should be looking at the voltage getting to about 3.6 volts. So I'm going to go on to pin 6 with my oscilloscope. Just going to change my value there, and I'm going to start my circuit. And you'll see something interesting here, because you will see the capacitor start to charge. So I press it, the LED comes on, and here we go, our capacitor is starting to charge. And it's got to 1 volt, 2 volts, 3 volts, 0.2, 0.4, there we go. It got to about 3.4 there. And you saw the voltage immediately discharge on pin 6 and pin 7 because they're connected together, and the LED went off. I'll do that one more time. Starting to charge, 1 volt, 2 volts, LED still on, 2.8, 3, 3.2, 3.4, there we go, 3.4 volts. That is how the 555 manages to charge and discharge at very precise levels. This is the end of activity 1. In activity 2, what we're going to do a little design and build task. So what I want you to do is to design and build a system that emits a noise for 5 seconds every time it is briefly cut off from light. So we're going to be using our original circuit. which is our monostable. But this time we are going to trigger it by some form of light activation, and the output is going to be something that emits a noise. So the first thing we're going to do, we're going to decide what component to use as the input transducer, then work out how to use it to trigger a monostable. So if we go back to our original circuit, used a pull-up resistor and a switch, so that when we press the switch the input went low, and that's very important here to recognize that we need to send a low to pin 2 to trigger our circuit. So in other words, something with light. Now we know from previous experience that an LDR with a pull down resistor will do fairly much what we need, because the output of that circuit, when light falls on the LDR, it will get somewhat darker. Sorry, when light stops falling on the LDR and it gets darker, we have a higher resistance across it, therefore a greater voltage drop, therefore the voltage should go down when it gets darker. And we want to send a low into the trigger pin of the 555. Now the question is, what values do we want to use? Well, first of all, let's look at the resistance value of an LDR in the dark and light, so we know what range of values we're going to use. So I have an LDR set up. I'm going to plug my meter in. I'm going to measure its resistance. So at the moment in the light, it measures 2.2 k ohms. And when I cover it up, it rises to 35 k ohms. So what value does this resistor need to be? Well, if this resistor was to be 2.2 k ohms, then we know that the voltage out will be 2.5 volts. Looking back at our circuit, we can assume that if we need to go low here, we may not need to go all the way down to 0. So if we assume that that value there is above and below 2.5 on the trigger point, even though I know that it needs to drop to about a third of that voltage, so let's say 1.6 volts, just putting in a 2.2 k ohm resistor may or may not do it. So the best way to do this is actually to put in a variable resistor that covers the range that we want. So we're going to be using it as a variable resistor and not as a potentiometer, so we're going to be using the middle leg and an outside one. So why don't we try a 5k resistor? A variable resistor, so we can adjust this between 0 and 5k. When it's 0 ohms, then of course this voltage will be 0, and when it's higher it will certainly be above the 2.5 volts because it's greater than the 2.2k. So I'm going to put my LDR into my circuit, and I'm going to connect up a voltmeter and look at the voltage at that point. Now the voltage at that point at the moment in the light is 3.61 volts. I can change it if I want to by changing my variable resistor, but let's put it as high as we can first, and then I'm going to cover up the LDR and you can see the voltage start to drop. Does it drop below half? Yes. Does it drop below 1.6? Yes, it does. So it's moving from 3.6 to 0.6 of a volt. Hopefully that will be good enough to trigger my circuit. So let's have a little look. Let's connect that part in, removing the switch and pull up resistor. So I'm going to see with the components that I have in there at the moment when I cover up the LDR, does my LED come on? Yes, it does. And when I take away, does it go off? Yes, it does. So that trigger part of the circuit works well. So the first part of our circuit can be a LDR with a variable resistor, no connection on the third leg, like so. Next, we need to work out our monostable time for a 5-second delay. Now if I go back to our original results, we can see that if we used a 100k resistor and a 100 microfarad capacitor, that gave us a time delay of 11 seconds, and we want about half that. Now we also know that when we doubled the value of the resistor, or we doubled the value of the capacitor, we doubled the value of the pulse length. So by definition, if we halve the value of the resistor or halve the value of the capacitor, we should halve that pulse length. So why not change the value of resistor, because we have far more of those available, and we'll halve that to 50k, except 50k is not a preferred value. The closest we can get to is 47k. So we know that 1.1 times R times C equals our time. So 1.1, and we're saying 47k times C, which was our 100 microfarad capacitor. What value does that give us? 1.1 times 47 exponent 3 times 100 exponent minus 6 gives us a 5.17 second time. Now I think that will be fine. That's only 0.17 of a way. So in our circuit we can use, on our 555, we can use a resistor value of 47k and a capacitor value of 100 microfarads. So following on from our circuit diagram, we can now redraw that portion of the circuit. So the resistor capacitor goes to pin 7, pin 6, 7 and 6. Our pin 2 is our trigger, which is now going to come from our LDR and our pull down resistor. We know that pin 1 is our 0-volt power supply. We know that pin 8 is our positive power supply. We know that our reset pin, pin 4, we connect to positive as well. And we know that our control pin, pin 5, is going to go via a 10 nanofarad capacitor down to 0 volts. All that we're left with now is our output, which is pin 3. And it asks us to work out something that will be turned on and emit a noise for 5 seconds. Now, what component can we use in our circuit to emit a noise? Well, previously we've used, for example, a loudspeaker, but a loudspeaker would not be suitable here because a loudspeaker needs a changing frequency. It was using the output of the oscillator to drive it. We have a 5-volt supply. Previously we have an LED here. The best component here would be a buzzer because it works directly off a DC voltage. So I'm going to connect to my output my buzzer. So I'm going to connect the positive to pin 3. I'm going to remove the LED and current limiting resistor. There we go. I'm going to pop that into there. I'm going to connect up the power to my circuit. And now, hopefully, when I break the light, the buzzer should come on. I remove my beam. It should stay on for about 5 seconds. That certainly sounded about 5 seconds. Shall we quickly measure that? So are we ready? And I've measured that to be 6. I was probably a bit slow. So now we have a circuit that matches all of the criteria to do with our specification that we've been set. And that's my circuit symbol for a buzzer. So I have a complete circuit diagram where I have my light circuit, which is triggering my monostable. So the low is going in, and we can indicate that by showing going from high to low. We have our resistor of 47k, our capacitor of 100 microfarads, giving us a 5.17 second delay. And the output remains high for 5.17 seconds, turning on our buzzer. After that, it goes off. Job done. This is the end of tutorial 14.